So towards the end of last lesson, this was what we talked about, differentiation from the first principle. And you could see that it's the combination of the gradient of tangents, which is this, okay? Because without the limit, this is just the gradient of the chord when you pick two random points, isn't it? So because the chord intersects at 2 points, by the time you break the gap between A and B, the tangent approaches the chord approaches the normal. Okay, approaches the tangent. Apologies. As you break the gap between the two, let me see if I have a picture. Yeah, not this one. Let's use the average stuff to do it. Yeah, this one. So you can see the chord AB, isn't it? You can see the chord AB. So there's a gap between A and B, but this time around we call it A and A plus H, where the gap is H. Similarly, this gap will be the gap between F of A and F of A plus H, isn't it? So as this gap approaches 0, which means as A and B come together, this secant or chord becomes a tangent. So think of this line as moving down. Are you with me? Think of it as this line is moving down. When this line moves down, these 2 points A and B will begin to come together, isn't it, on the curve? And consequently, this chord automatically becomes a tangent to the curve. And the gradient of the tangent to the curve is actually the gradient of the curve at that particular point. Is that understood? So that is the idea we will be looking at. Mr. Chang, any problem? Okay, just to do a recap of the last stuff that we did. So we are combining this gradient of tangents with the definition we learned here, gradient of tangent, and then we learned the definition of gradient function. The gradient function is used, like I said in the class, when you do not have a linear function. If you have a linear function, the gradient does not give a function, the gradient gives a constant. Because for any straight line, the gradient at different points is the same. Does that make sense? But for a curve, the gradient at different points varies. So because the gradient varies, then we can describe the gradient as a function, some function g, for example, such that when x is 1, you get a different gradient. When x is 2, you get a different gradient. So that function that describes the gradient at any point x is the gradient function of f, and that is represented by the symbol f dash x. Some call it f prime x. It doesn't matter. Does it make sense? So the gradient at any point, because you can draw the tangent at any point, right? Coupled with the previous knowledge is what we now use here in the first principle. Okay, so if the limit exists, then f prime of a is equal to the limit of this, which is the gradient of the tangent to this function at this point. I hope this is clear enough. Yes? All right. Okay, I probably need to close my WeChat or tell from 5 to stop talking. They won't stop talking. I'm supposed to take them today, but I think I'm tired, so. And they are not in a hurry yet, so there's no need to teach them extra. Anyway, so so this is just the old thing that we have mentioned, being repeated on this page. Since we're using the book mostly on Zoom, I'm just going to go through it like that. Let A and B with this coordinate. So if the coordinate of A is A for the x-axis, then the y-axis will be f of A because the function is f of x, right? Sorry, x and f of x. Similarly, this will be x plus h. Then this will be f of x plus h, isn't it? So if you look at it, the gap is this one and the gap here is h. So gradient of this chord is that. But as this curve, as the gap here approaches 0, this curve approaches the tangent to the curve. All right? And we already said the gradient of the tangent is the limit to this. We have done this before. So this is just a repetition of what we said. Now, if we are using the first principle, this is an example. So I'm going to play this self-tutor like I always do. And it's just expansion and limit. It's so easy. Let me see if I'm sharing the audio of the computer. Of course not. All right, so let's play this. Just listen attentively and ask me questions if you have any.
We have previously used limits to find the gradient of a tangent to a function f of x at a particular point. We can apply this method to a general point to find the derivative or gradient function f dashed of x. We call this method first principles. The derivative function of f of x is defined by this formula. To obtain f of x plus h, we substitute x plus h in place of x in the function for f of x.
You can't see anything?
We can use the binomial expansion to expand the...
Uh-oh, sorry. Thank you, Ethan. Sorry. Okay, I just saw that. How about now? Okay. If somebody just give me a sign next time. Just say, hey, emergency, hello. But you can hear the audio, right? Okay, all right, let's start again. Thank you, Mr. Chang.
We have previously used limits to find the gradient of a tangent to a function f of x at a particular point. We can apply this method to a general point to find the derivative or gradient function f dashed of x. We call this method first principles. The derivative function of f of x is defined by this formula. To obtain f of x plus h, we substitute x plus h in place of x in the function for f of x. We can use the binomial expansion to expand the brackets, then simplify the result. Notice that every term in the numerator contains h, so we can remove this as a common factor. We can then cancel the factor of h, since h does not equal 0. As h approaches 0, the terms containing h, h squared, and h cubed will also approach 0. Therefore, the derivative function is 4x cubed. Once we have found the derivative of a function f of x, we can evaluate the derivative function for a particular value of x. This gives us the gradient of the tangent to f of x at that value of x. To find f dashed of minus 1, we substitute minus 1 into the derivative function. The result is minus 4. This means that the tangent to the function at the point where x equals minus 1 has gradient minus 4. We can illustrate the result on a graph. Notice that the tangent has a steep negative gradient.
Does this make sense? So this is what the first principle is about. Just remember this. That is why we started from the beginning, so you know what we mean by this symbol and how this came about. Again, the gradient of a curve at any particular point is the gradient of the tangent to the curve at that particular point. Does that make sense? The gradient of this function, x to the power 4, at x equals negative 1. Again, the gradient of this curve, the black one, at x equals negative 1 is simply the gradient of this green tangent at x equals negative 1. That we have done from middle school up to IGCSE, but so it's the same idea we are adopting here. Okay, that is why when finding the gradient of the curve, we simply just find the gradient of the tangent to the curve. And we have seen why this limit gives the gradient of tangent to the curve. Because it started from a chord, okay? And for the chord to become a tangent, the 2 points of intersection must be just 1 point of intersection. And that can only be done if there is no gap between the 2 points on the x coordinates. Does that make sense? That is why we take the limit as h approaches 0. H is the gap between them. When h approaches 0 means when the 2 points merge Whether A goes to B or B goes to A or both meet somewhere in between, nobody cares as long as H approaches 0. Does that make sense? So without this limit, this is simply the gradient of the chord. Okay, now we are saying the gradient of the chord becomes the gradient of the tangent when the gap between the 2 points in question becomes 0. That's just like commonsensical statement. It's nothing here that was maybe brought from the space or anything. Does that make sense to everyone? Okay, so and that is where this whole idea of first principles come from. So you'll be given different functions. All you have to do is remember this. Always state this first. Okay, by first principle, f prime of x is given by limit of blah blah blah. Then you already know your function. You substitute. This is simply substitution of function. Okay, then you use your binomial expansion. You learned in topic 1. You simplify. Now everything we have done here is just the normal limit. Remember, you can substitute directly in limits if you do not get undefined. But whenever you notice that if you substitute 0 directly, there will be 0 at the bottom, right? So what do we do in the class? We factorize h out, isn't it? So it's just, like I told you, it's just a bunch of previous ideas being put together to bring up something new. There's nothing new here. There is absolutely nothing new here, just different names. Oh, it was called this in the past. Now we're going to use it for something. We produce another, we use the raw material, produce something else, and give it a different name. That's just it, nothing different. Okay, and after getting the f prime x to be this, getting this simply means, now this is the gradient of this function f. Can you see my cursor? Gradient of this function f at any point x is given by 4x cubed. So if the point is -1, then this will be the gradient. If the point is 0, the gradient will be different. Does that make sense now? And clearly, when the point is 0, the gradient will be 0. And you can see that already here. Can you see why there's no gradient? There is a change in x, but there's no change in y. Can you see at 0, if you draw any tangent, the tangent will just be your x-axis. That is why we say at the turning point, the gradient is 0. Does that make sense? So, having said that, oh, I forgot I was sharing that. Miss K, any problem? Krista C, any problem? Krista K. Sorry, I had to call everybody's name because I couldn't see everybody on one screen. Callista. Okay, good. For the rest of you, I saw your face already. Just the people that didn't see their faces immediately. Now, so that is that about this. It's a short class, like I said. Now, let's look at this. So Leibniz came up with a notation. So I want you to also put that in your notes after, like a continuation of what we did yesterday. So by Leibniz notation, if the function, if f of x is a function, we know that this represents the derivative of the function. The Leibniz notation is that this f dash of x is written by dy dx. So most of you must have heard dy by dx, dy by dx is the same with your f dash of x. It's just the general notation here and a notation given by Leibniz. Leibniz and Newton were one of the founding fathers of calculus, actually. I think according to history, there was this issue between, I think one of them is French and one of them is an English mathematician. It's like somebody discovered something and wouldn't publish on time, according to the history I read, if I still remember the story correctly. So take, for example, I discovered something, but I haven't published it, either for any reason. It could be for genuine reasons, still investigating, or for my own selfish interest. I do not want to expose the information to the world yet, probably to make myself look like the king of the whole planet. I don't know, whatever the reason was. And over time, the other person was working on it, and the other person published the result. Then it became like a kind of war between mathematical communities in the two countries. Oh, he stole our idea. I think it's more like the China-US war on technology theft these days. Oh, they stole our idea, they made it look like this and all that. So there was this friction between Leibniz and their fans, as well as as the Newton back in the days, according to the history. Anyways, so Leibniz has a notation, and that is dy dx. So we could not d of y, d of x, just call it dy dx. It's read this way. So this notation is called the Leibniz notation. So whether you write f prime of x or you write dy by dx, what you're talking about is the gradient of that function at any point x. Does that make sense? So we'll be using both notations interchangeably. Also, we can do this again in a different form. I think Krista K was using a notation, and I said, don't use that notation yet. So this is where you must have read some literatures to be able to write like that. So now listen very well. The same illustration we have given before. In fact, this was illustration I used to give some college students. We call it a polytechnic in Nigeria. When I was teaching them first principle and calculus, I always begin with this similar diagram. So there is a point x. This delta is like a small change. Okay, a small change. It's a Greek, no, not Greek. Come on, Greek letter. Yeah, I'm right. It's Greek letter. It's a Greek letter, just like alpha, beta, gamma. Delta is the fourth one, just like our A, B, C, D in the English alphabet. So delta means a change. And this is just the lower case. The upper case is that triangle symbol. I'm sure everybody know that. And those of you doing economics, Mr. Cheng especially, you must be using some of this delta a lot in some of your stuff. So delta means change. Even in physics, you must have done change in something divided by change in something. You must have done something on maybe capacity, its capacity, MC theta. Okay, and that theta is change in temperature, if I'm not mistaken. So there are some situations, and even in physics, we use that symbol. So delta y, delta x means this change along the y and the change along the x, respectively. So in that case, instead of using h, we can say, okay, as this, we can say, okay, for this chord here, if we draw a chord from here to here, to become a tangent, delta x must approach 0. Do you understand the point? So instead of h now, we call that change delta x. Why do we call it delta x? Change in the x-axis. Similarly, delta y will be change in the y-axis. That's just what it means, just notation, because delta means change in something. Understand? So in this case now, we call this y f of x, and this will be f of x plus delta x, which is more or less, if this is y, then this is just y plus delta y. It's the same thing, just written in the different form. Okay, so using the Leibniz notation, we can rewrite what we had before. So the gradient of the chord, which is this. When I say this, I mean without the limit. All right, the gradient of the chord will be simply this minus this, which is this, no, sorry, it will be this first. Change in y, which is delta y, divided by change in x, which is delta x. Am I making sense? So that is why this whole notation was written again. So this one is actually this. Hello, please talk to me if you are getting what I'm saying. Can I see some hand wave if you understand what I'm saying? Okay, Karen is confused. Okay, she's waving her hand now. All right, thank you. I just need to be sure. You're just saying it in a different way. You don't have to worry about it. But if it was mentioned or you are reading some textbook somewhere or something came up in your physics or chemistry experiment, then you know what it means. That's the whole point of mentioning this. Okay, so we're just rewriting the previous notation that we have written. So this is the gradient of the chord, and the chord is simply the difference between this one and this one, along the y and along the x. But that difference has already been written in notation. Change difference in y is delta y. Difference in x is delta x. So everything here is actually everything here. So if you want to get your f dash of x, it is simply as the gap becomes 0. In this case, the gap is delta x. So that is why the limit is now as delta x tends to 0. So it's the same thing. Okay, so basically dy by dx is the limit of delta y over delta x as delta x tends to 0. That's what we are trying to say. Understand? But you don't need to, you don't have to do your workings in this form. You can just stick to the previous one. Understood? All right. So I wanted to, yes, sir.
What do you mean by we can just go back to what we did before?
I go back to what we did before?
Yeah, not like you said we don't need to do the workings for this. We can just go back to
Like you don't have to use delta y, delta x notation. You can use the notation in the example that I just showed you in this example, which is just using the h and the stuff, not delta. You don't have to bring the Leibniz notation in. Okay, but towards the end, you can write dy by dx is equal to is fine. I'm saying you don't have to use limit because if I want to do this same question, I could use the delta y delta x notation, but that would be more complicated for you. In fact, in the past, that's what I always use. Do you understand what I mean? I'm saying just stick to this. Understand? Don't bother using delta y over delta x. Because this is what that will look like. Let me show you. Maybe you can understand what I mean. Okay, Arinze, not now. What is this? Yes! Sorry, guys. Nice. Arinze got an award in hymns. Sorry, my cousin studying for math just shared the good news with me. All right, okay, we'll talk about that later. Sorry, I'm just happy. Outstanding something student. That's wonderful. Okay, let me go to the board. Okay, I read this message. You will have seen red. Be right back. I'm in Zoom class. Professor. So limit your f prime of x is simply the limits as h tends to 0 of fx plus h minus f of x divided by h. Okay? So if I'm to find, for example, the gradient function of y, or you can call it f of x, is equal to x squared, for example. Okay, f prime of x will be limits h tends to 0. This is f of x. F of x plus h will be what? X plus h squared. You understand? Minus x squared divided by h. Again, maintain the limit until you are ready for your substitution. So by Pythagoras, not Pythagoras, why do I keep saying rubbish? By binomial expansion, yeah? Then we have also minus x squared, everything over h. This and this cancels. If this is a binomial, maybe plus a, don't forget your brackets, okay? Because some of the work you'll be doing will not just be a monomial. Monomial is too cheap. Okay, so this will be, my numerator becomes 2xh plus h squared divided by h. So this looks like your normal limit that you have done in school, right? So you show, of course, how you bring that out. 2x plus 1h divided by h. So everything becomes limits. See, the substitution is not done until the end. So that's just a function. It's a polynomial now. It's no longer a rational function. So I just put it in brackets. So when I substitute that h, I get 2x plus 0, which is equal to 2x. Now that's the notation you know. If I'm to use the delta y over delta x notation, so I'll be saying from f of x equals x squared, and I'll be dealing with x plus delta x instead of h. That's just the difference. Then that will be x plus delta x squared. Can you see that? So now I'll be doing I'll be saying limits, which is my f dy by dx, is simply limit of delta y over delta x as delta x tends to 0. Okay? Now, just a sec. Now, my delta y over delta x, according to this, so if I have a curve here, the change along here is my delta x, and the change along here is my delta y. So if this is my f of x, then this should be my f of x plus delta y. Agreed? So maybe I should use that instead. Such that, how do I do this? Let's see. Okay, usually this will not be the first thing. Let's start with the gradient. The gradient of the curve is delta y over delta x, change in y over change in x, and to get the change in y divided by change in x, in terms of the function, I'll be having f of x plus delta y minus f of x, which is the same. Now, I think x plus delta x should have been the approach, sorry. So I have f of x equals x squared, sorry. F of x equals x squared, and so I have f of x plus delta x will simply be x plus delta x all squared. So if I open this bracket, x squared 2x delta x plus delta x squared. Can you see that? Okay. And remember, I have my f of x also as x squared. So the difference between these two is the difference between these two. Agreed? Talk to me, please. Okay, it's like subtracting. Okay, if I subtract now, my f of x plus f of x plus delta x minus f of x, this is on the left hand side. On the right hand side is simply x squared plus 2x delta x plus delta x squared minus x squared. Do you agree? So this is your what? Delta what? Talk to me. This is delta what?
Y.
Say that again.
Delta y.
Exactly. You see, this is a change in y, isn't it? Remember, f of something is the y coordinates. If you have your curve like this is your x. This is f of x. So when you say f of something, you're talking about y-axis. Okay? So the difference between this coordinate and this point is actually the change in the y-axis eventually. That's what I'm trying to say. Can you see? Okay, so clearly this is just 2x delta x plus delta x squared. So now I'm going to divide delta x on both sides. So I have delta y divided by delta x. This is going to be 2x plus 1 delta x, correct? So it is at this point that I introduce my limits. So if I take the limit of both sides, limit as delta x tends to 0, limit as delta x tends to 0. Okay? On this side, I have delta y over delta x. On this side, I have 2x plus delta x. All right? And by what you have seen, this whole thing here is dy dx from that Leibniz notation that I showed you. So this is dy dx on the left. Are you with me? And on the right-hand side, this whole thing is just normal limit evaluation, which is 2x plus 0, and that is 2x. So the problem is most people, to manipulate these, usually it's not stressful. So you have your function, you evaluate the function with delta x first. Instead of saying f of x plus h, you just do f of x plus delta x. Simplify that, then find the difference between f of x and f of x plus delta x. That is automatically your delta y. Understood? Then form this fraction by dividing both delta x from both sides, and that's it. So this notation sometimes might be confusing. This looks like a direct approach. Do you understand? Or which one do you think is more direct to you, the first or the second? Talk to me, guys. Is this one direct, the first, or the second one? Hello, can everybody hear me?
Yes.
Any conversation? The first
First.
or the
This is, we
second?
need to think.
Oh, okay, he needs to think. If you don't need to think, tell me.
I think the first.
The first one, Karen thinks first one, yes?
The first one.
First one. Yeah,
Can you
two
show the second
people.
one again?
What?
Can you show the second one again? Yeah, I think the first one is simpler.
So the first one is more direct. The second might be more kind of complicated. But it's actually the same thing and it's not difficult, really. But the first one looks more a direct approach. It's like the first one involves a formula that has been done already. You just have to substitute and simplify. But in the second case, you have to be the one to establish the fraction with the limits to take. So it's like you have to come up with this yourself. You are not just doing the limit. You have to come up with this step, subtract, divide from both sides, then also come up with this yourself. So it's like you have to do 4 different things before you substitute your limit. But in the other one, you just do limits, stay from the beginning because of this formula that has been created for you already. Understand? So that's why I think the first one is more direct. So, which is why I won't recommend the second one. Of course, you are welcome to use it. But if you read some papers and you come across this, then you should understand why it is done that way. Okay? All right. So,
Mr. Daniel.
Yes, sir. Quickly.
Can you post this screen right now?
I will. I just saved it. I just saved
Okay.
it. So I'll be sending it to the stuff. So let's take an example from the book. And that example I'll probably do in both ways, just to give you an idea what the 2 approaches look like, all right? So let's pick a more general function like this one. Can you see? Let's take a trinomial. Find dy by dx from first principle is the same thing as find f dash of x from first principle. I hope everybody is aware of that now. It's the same thing.
Are you showing the textbook right now, Mr. Daniel?
Oh, okay. Sorry.
I can only see the
Sorry, I keep forgetting. So find f prime of x. I call it f prime of x sometimes, but f dash x, it doesn't matter. But don't call it f of x, all right? Finding this and finding this is the same thing. The only difference is we use the Leibniz notation to denote our gradient function. That's it. It's the same thing we are talking about, all right? So which do you prefer I do? 2C or 3B? Yes, 2C or 3B?
3B.
3B, one person said 3B. Yes, let's hear from others. Put in the chat, 2C or 3B. Let's see what most people prefer. 2C or 3B, quickly. Put in the Zoom chat. 3B, 3B, 3B. Okay, I think everybody wants 3B. Why? Does it look difficult? All right, so let's do 3B. Let's do 3B together now. So first principle example. So the question says 2x squared plus x minus 1. Y equals 2x squared plus x minus 1. Now, if you look at the question, it says find dy by dx, so they put it in form of y. So it makes sense to say find dy by dx. So listen to this notation, everyone. Dy by dx simply means the function is y. If the function is p, we will say dp by dx. If you are working on economics problem, where I think pi is used to represent the profit function, it will be d pi dx, if x is, of course, the independent variable. Understand? When we get to motion problem, we'll be talking about ds dt. derivative of the distance or displacement with time. So the x, this t will be our velocity. Okay, we'll say velocity, speed, whichever one we'll call it later, will be the actually the speed will be displacement with time. That's what it means, ds dt. Okay, now so we take note of all that. But if you call it f of x, this is how you can write it. If the function was given to you as f of x, you have two options, f dash of x or d dx of f of x. This is also allowed. Derivative with respect to x of this function. Does that make sense? Just like derivative with respect to x of y. That is what we now write as dy dx. It's like a fraction, just like you saying half of p, or let's say 3/2 of p. Isn't that a way of saying 3p/2? So they are just symbols, okay? So anyways, let's get rid of this. So because it is called y, it means I will leave my answer as dy dx, okay? But if the function was called f of x, I will leave it as f dash of x. Can you get the difference? But if you use them interchangeably, you call it to dy by dx, I don't think you should be penalized. Okay, so now I'll first use the simple approach. For the simple approach, because nobody called it f of x, I'm just going to say let y be f of x. Okay, if I call y f of x, then my dy by dx is simply the limits as h tends to 0 of f of x plus h minus f of x divided by h. Can you see what I did? I didn't call it f dash of x. I call it dy by dx straight up. The reason I introduced this is because there is no way I can write this numerator if I do not bring in the notation f of x. Does that make sense now? And y could be g of x, it could be h of x. So if I'm using f of x, I should state it clearly that my y is now being called f of x. Does that make sense? Just a little detail. So this will be the limits as h tends to 0. My f of x plus h will be 2 brackets x plus h squared plus x plus h minus 1. Understood? Then my f of x, because my f of x is a trinomial, it has to be in brackets. If you do not put it in brackets, you're going to make a mistake. Okay, sorry guys, I need to close my WhatsApp. Okay, so let's move on. This is limits as h tends to 0. I expand this bracket. Power first before multiplication. Bird mass or bid mass. Grade 5, grade 6. So which means you have to expand before you multiply in. X squared 2xh plus h squared. Can you see that? And this remains x h minus 1. Then we open the bracket, minus 2x squared minus x plus 1. Understood? Everything divided by h. You see, while simplifying, I have my limits, and I'm just trying to, this is h, sorry, not x. So I open this bracket, I have 2x squared, 4xh, 2h squared, x h minus 1. Actually, minus 1 and plus 1 can cancel now, but let's just write. Okay. So when I remove the stuff that can cancel, this goes. I have x also. And I have 1 and negative 1. At the end, I have limits as h tends to 0. My numerator now is 4xh, 2h squared plus h divided by h. Okay, so which is limits as h tends to 0, h bracket 4x plus 2h plus 1. Okay, which is the same as limits as h tends to 0 of a polynomial now, 4x plus 2h plus 1. Now this is just direct substitution, 4x plus 2 times 0 plus 1. So finally, your answer dy by dx is simply 4x plus 1. Does that make sense? Now, one thing you should notice, at the point of substitution, after you cancel here at this point, when you cancel, the only terms that are left contain h. Otherwise, h cannot be factorized. Do you agree with me? So you have to be careful. The only terms that are left will contain h. So that's that. Let's look at another one, or maybe I use the delta notation now. I call it f of x already. 2x squared plus x minus 1. Okay, so from here, find your f of x plus delta x. And that is 2x plus delta x all squared plus x plus delta x minus 1. Agree? And this is simply 2x squared plus 2x delta x plus delta x squared. Delta x is one symbol, so that's why I put a bracket. Understand? Then plus x plus delta x minus 1. This is simply 2x squared plus 4x delta x plus 2 delta x squared plus x plus delta x minus 1. So from here now, you find f of x plus delta x minus f of x. So which means everything here minus everything here. Understand? So you can write that out, or you can just write the results. But I'm going to write it out so we can see. My handwriting looks horrible. Sorry. So minus all this. So if I open the bracket, I'm just going to write the result now. If I open the bracket, -2 plus x and minus 1 goes. Understand? So it means f of x plus delta x minus f of x. Okay, I'm going to write it again. Sorry. To delta x all squared x plus delta x minus 1 minus 2x squared minus x plus 1. So at the end, this left-hand side is simply change in y. And what is left on the right-hand side is simply 4x delta x plus 2 delta x squared plus delta x. Do you agree? Because every other thing is gone. 2x squared is gone. Let's see. This 2x squared cancelled here. This plus x cancels minus x. This cancels this also. So we are left with this one, and this one. Just 3. Okay? So what we're going to do next is divide through by delta x. If we divide through by delta x, delta y divided by delta x, is simply 4x plus 2. There's no need for bracket anymore. There's no square anymore. Plus 1. Can you see that? So the next is to take the limit of both sides as delta x tends to 0. Also here, you take the limits as delta x tends to 0. What were the original function, original stuff there? Delta y divided by delta x. While this is a polynomial-like expression. Okay. At this point, this left-hand side, I'm using different colors so we can trace them. Let's write the left-hand side in green. This left-hand side is our dy dx. Agree? So the left-hand side is just change the notation. The right-hand side is evaluate the limits. Okay, this right-hand side here, we should just evaluate the limits. 4x plus 2 times 0 plus 1. Can you see that? Because delta x is like as x tends to 0 that we keep using. Understand? So finally, dy by dx is simply 4x plus 1. The same answer, different approaches. I used this for years. I just started using this a few years ago. It's the same thing. I've used this for more than 10 years. Even though it looks complex. But to me, it's easy because I just need to evaluate this, evaluate that, simplify, and stuff. But this, because it's just a direct formula. So either way, it's fine. Your choice. Okay? I'll just go through 2 more examples. Then you will have your time to practice on your own. I created a worksheet already. I was going to give you that worksheet in school. I'm happy to send you a picture of it, or you just practice in your book and I give you the worksheet later. Okay, just practicing. I'll send you a screenshot of the book, then I'll give you the worksheet later because it's a graded worksheet. So you just submit to me later. Now, for polynomial-like structures, you can see that there is it's just direct substitution. I'm not sure, but what if IB gives you a rational function? Okay, for example, find the derivative of this function, y equals 2 over x. And the same thing will happen to maybe x squared or x cubed. So I'm just going to do 2 over x just to show you what needs to be done. Okay, now using the delta notation, I've used that in the past for something like this. Using the delta notation, again, I'm just going to do x plus delta x, which is going to be 2 divided by x plus delta x. And there's no expansion here. Agree? After, there's no way we can simplify this. Do you all agree with that? So after this, so the next thing we always do is the difference between f of x plus delta x and f of x. Can you see that? And that is just 2 over x plus delta x minus 2 over x. Did you see it? All we have to do is match them as a single polynomial. You agree this will be 2x, then 2x plus delta x. Agree? So this is simply x plus delta x. This is 2x minus 2 delta x. And that gives you negative 2 delta x divided by width. All right? Properly. So this is still f of x plus delta x minus f of x, right? And we all know that this simply means what? Everyone. This simply means what?
Delta y.
Delta y. So I can write delta y as negative 2 delta x divided by x bracket x plus delta x. Do you agree? So what I'm going to do here, because I'm not going to say divide both sides, I'm just saying multiply by 1 over delta x. So which is just delta y divided by delta x, not dy, please. And this will be -2 divided by x plus delta x. And if you cross multiply, you're going to get this again. You agree? Karen? Agreed? Okay, so from here, take the limits of both sides. As simple as ABC. Once you get to this point, the next thing is limit. So limit delta y over delta x as delta x tends to 0, which will become dy dx in the next step. It's simply the limits as delta x tends to 0 of this fraction. Of course, because this limit exists, we have x plus 0, -2. Can you see that? Then your dy dx is simply -2 over x squared. Okay, so you can try the same question using the other approach. All you have to do is, again, dy dx, f of x plus h minus f of x divided by h. That's all. And you simplify. So one way or the other, your h, just like this delta x, will be extracted one way or the other, and you can do what you need to do. So you should try that for this same question on your own later. Okay, for this same question. I'm using the old method that I used so that you can master the new method that I'm introducing to you, which is the one in your textbook. Understand? The last but not the least, because I don't want to go into this when we come back. And it's not difficult, so there's no point wasting time. Sometimes you can be given a function that is a surd. I'm not sure if that is in the book. Yeah, it's in the book. It's actually question 10. Okay, maybe I'll let you practice that. Okay, I'll let you practice that, but we're going to do cosine together. Look at this question 13. I'm going to send something to the WeChat now. I hope it's not the question in my worksheets. Allow me to check the worksheets first, guys. Because one is in the worksheets, one I planned that we do in class together. Understand? So let me see. Differentiation by first principle. Let's see. Okay, sine is in the worksheets. Cosine is not in the worksheets. Perfect. Okay, great, 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 great. So I sent something to the WeChat now. So I'm looking at that question 13. Question 13 from page, what page is that? Page 430. Page 430. So what does the question say? Show that, I think everybody should be able to do that, right? Show that cos A plus B minus cos A minus B equals that. Let's just solve everything together. I gave you something similar in the worksheet. So let's just do this together. Understand? And now I need everyone's contribution. So if you don't mind, please turn on your mic and talk to me as I work. So we want to show the A parts. We want to show that cos A plus B minus what? Minus what? Cos A minus B. Someone should talk to me, please. Is equal to something. So let's start from here. Yes, what is this? You forgot your addition angle. Come on. What is cos A plus cos A cos B? Cos A plus B. Who's speaking? Hello, is that Lily? All right, I'm listening. What is cos A plus B?
Cos A, cos B,
Mm-hmm.
sin A, sin B.
Minus sine A, sine B, yes. And for the cos A minus B will be?
A, cos B plus.
Uh-huh. Okay. So if we open this bracket, we get cos A cos B minus sine A sine B, then minus cos A cos B minus sine A sine B. That gives minus 2 sine A sine B as required. So that's the end of the first one. Yes? By letting S be A plus B and D be A minus B. So the second question, let S be A plus B and D be A minus B. That S stands for sum and D stands for difference, I think. We want to show that cos A minus cos D is equal to something. So you just substitute, okay, from what we have done, from A, cos A plus B minus cos A minus B is simply negative 2 sine A plus sine A and sine B, right? Right? But then if we substitute S here and D here, we don't have anything for A and B yet. All right? So Nakita, what do you suggest?
We should substitute S and D first.
But if we are going to substitute, because this is one line, remember, this is equal to this is one line. So everything has to be ready before we substitute. But we have A plus B, which is S, A minus D, which is that, but we don't have A and B. What do we do?
Oh, we divide them.
Divide what?
We should divide them like A and B times divided by 1 over A or something.
Not quite. Not quite. Why do we need to divide? Are we suggesting they are the same value? A could be 10 and B could be 80. Mr. Chang, what do you think?
I think I know what she's trying to say.
Say that again?
Like, I think I know what she's trying to say. So, first we need to get sine A, right?
Yeah.
So you agree with me that sine A is the same as sine A plus B plus A minus B, everything divided by 2.
Yes. But that's like going a longer route. All you have to do is solve this simultaneous equation because you already have a simultaneous equation. Okay, if you let this be this, then look, this is what we just need to do. You probably will get it, and I don't know if you will be penalized for doing wrong thing or for not doing or for doing, or maybe you did the right thing, I don't know. But it looks like too complicated. Can you see this? That's all we have to do. Understand? Nakita, understand? So I think both of you are going too far with the way you were reasoning about it. So if you do the same thing, but this time around, we want to subtract instead of add. Then A disappears, then we have 2B. You see that? Okay. So now you could see that we have A, we have B, we have S, and we have D. Understand? So with this, we can say that, oh, from A, what is the result from A? Cos a plus b minus cos a minus b, which is equal to -2 sine a. This is why a has to be obtained. Understand? Then sine b, this is why we obtain b as well. From that, it implies that cos what? Let's do it together now, quickly.
S.
Say that again.
S.
S.
Minus cos D.
Good. Equals
Minus 2 sine S plus D over 2.
exactly. So we just substitution. Then sine S minus D over 2. Understand? So that's all we have to do for that. Nice try, everyone. So we've done that. Hence, find the derivative of cos theta. So you might be wondering, why do we have to go through all this because of derivative of cos theta? No worries. So we want to find the derivative of y equals cos theta. No, cos x, sorry. So let's y be f of x, which is equal to cos x, right? Then our f of x plus h is simply cos what? X plus h. Can you see that? Talk to me, please. Yes? Okay, great. So our derivative, do we call it d something or f of something? Oh, f of x. They call it f of x already, so we don't need to let. So from our f of x equals cos x, then f of that will be that. Okay? So we know that the derivative is simply the limit as h tends to 0 of f of x plus h minus f of x divided by h. So this will be the limit as h tends to 0 of cos x plus h minus cos x divided by h. Can you see why we had to do this now? So if you have difference, you can change it to product of signs. Can you see that, everyone? So this time around, our s and d are now our x plus h and h and x. Agree? All right, so let's go to the next page. So I can say that, but cos s minus cos d is equal to -2 sine s plus d over 2 sine s minus d over 2. Okay, so it implies that I could just simplify this first before putting it back. So, but you have to be careful how you write. So let's do this together now, everyone. What would this be now? Yes? Come on, come on, come on.
Wait.
I'm listening. Others are
Yeah.
quiet. Karen, Verna, Callista, Krista. Yes? Talk to me, please.
-2 sine.
-2 sine. Mr. Chang, you were talking before, then you kept quiet to give others a chance. Speak.
And then x plus h. And then what was it?
Agreed?
Yeah.
And this is x plus h minus x over 2. Am I right? So this will be -2 sine 2x plus h over 2, yes, and sine h over 2. Is that?
Yes.
Okay. Now, I don't know if you can see something that I'm seeing. So if you put this back, so our f prime of x is simply limits as h tends to 0 of minus 2 sine 2x plus h over 2 sine h over 2 divided by h. How do we proceed? How do we proceed?
I think you would split the fraction
Into what?
parts, right?
Split how?
And then minus 2 times sine 2x plus h over 2 over h. Wait, no, not yeah. And then times sine h over 2.
Any other idea? Nice try, mister.
But something like that.
What? What do you say?
Something like that. It's hard for me to say. I'd rather just write it down.
You're not saying something. You should connect it to something we did recently.
The sine x over x.
Yep.
And then
Connect.
split the -2 with
Say that again.
split the -2 with the side h over 2. So when you divide it by 2, it cancels out.
Yep. So tell me what the next step will look like.
Sine h.
9h.
2x plus h divided by 2.
Okay.
Divided by h. I mean, you would put the -2 with that too, right?
You don't have to.
Because if you put it together, that 2 would just...
Actually, the negative can come out of... Oh, did Krista leave the room? Krista, what's going on?
I think she has the Wi-Fi issue.
Oh, okay. I had it now. Actually, our negative can be here. So this can be h over 2. Can you see? Oh, h over 2. And the other limit could be can you see this? Right? When h approaches 0, h over 2 also approaches 0, right? Karen, you can see something already? You remember the fundamental limits for trig? Okay? So what we are trying to use is this idea. Approaches what? As theta approaches 0. This approaches what?
1.
1. That's what we are trying to use. Remember this. Talk to me, guys. Do you remember this?
Yeah.
Okay. So I'm going to write it again as limits as h over 2 tends to 0 sine h over 2 divided by h over 2, which will give me -1. Why this is just direct substitution. Why can I substitute directly? Because if this approaches 0, everything approach sine 2x over x. So the limit exists that way. Understand? And that will be sine x. So that should be 2, sorry, not x. This will be sine x. Can you see that? Such that the final result is f dash of x is negative sine x. And this is the last result. Any questions? So this is the last result. You can try similarly. Oh, Karen was just here and it shows Karen again. What's going on with CTM? Hello, is everyone here? Sorry. Is Krista back? Krista, what happened? Internet? Karen also lost signal. Anyway, we're done. I just needed to go back to that board and show you what I just did. Can everybody see the board? Except Karen. Hopefully she get it together soon. So look at it and ask me questions. Look at it quickly and ask me questions. So if you want to do it, I will encourage that at this point, you can state the reason. Okay, so because, Bena likes to write because this way. Very smart. Because limits as theta tends to 0 of sine theta over theta is equal to 1. So this angle is at the bottom, is also tending to 0. That's why we had to change it here. Okay, so that's how, there's a step for this one. The previous step, the reason we are able to write this here, you can write it here, because as h tends to 0, h over 2 also tends to 0. That's the reason for this one. Okay, and the reason for this one, I use different colors so we can trace it. Does that make sense, guys? So similarly, you can try that of cosine. Is Karen back? I don't think so. Maybe she still has internet problem, but it's okay. So this is all about first principles. The rest is just for you to do practice. Okay, I'll send you pictures of the page of the book because nobody expects this holiday. So you probably don't have your book with you. I'll send you all the examples also. And that's it. Okay. All right. All the best. Sin x, blah, blah, blah. There's another way actually this was done. Oh, please, let's listen to this example as the last one. There's an example from the book. So I want you to hear the explanation. Let's stop share for this one. After this, we can call it a day. Karen is trying to join back. Hopefully she will be able to. Otherwise, she will watch this stuff later. So let's look at this example. So there's one of the question, this in the exercise also that I gave you. I actually asked you to do this question. Question 12. I gave you question 12. Okay. I can kind of modify question 12. I said, prove this, then use that to do sine or something. I can't remember how I put it, but it's not like this question directly. So, but let's see how this limit became 0. The limit we know is that limit of sine h over h as h tends to 0 is 1, right? But now this looks like another result. So, but that is discussed in the previous stuff. So let's see quickly. This time around, I need to share the pop-up with you. Can everybody see the pop-up? So let's see if Karen is back. Yeah, she seems not to be back. Uh-oh. She's struggling. All right, I'll talk to her while you're listening to this, and I'm sure she can catch up later. Okay. All right, so let's do this quickly. 1, 2, go.
In this example, we use first principles to find the derivative of the trigonometric function sine x. However, before we do this, we are asked to prove that a particular limit is equal to 0. We will need this limit for calculating the derivative. Look at the limit. Notice that as h tends to 0, the numerator tends to 0, and the denominator tends to 0. For any trigonometric limit like this, we need to rely on the fundamental trigonometric limit, sine theta over theta. We already have the angle h in the denominator, so we need a way to get sine h as a factor in the numerator. Suppose we multiply the fraction by cos h plus 1 over cos h plus 1. When h equals 0, this is 2 over 2, so we are certainly not dividing by 0 and creating more problems. In the numerator, we now have the difference between two squares. Using the Pythagorean identity, cos squared h minus 1 is equal to minus sine squared h. We now have the factor sine h in the numerator, which is what we wanted. From the limit laws, the limit of the product of two functions is the product of their limits, provided both limits exist. So, we have the limit of sine h over h, and all of the remaining factors go in the second limit. The first limit is the fundamental trigonometric limit. As h tends to 0, minus sine h tends to 0, and cos h plus 1 tends to 2, so the second limit tends to 0. So we can conclude that the limit as h tends to 0 of cos h minus 1 all over h is equal to 0. We are now ready to differentiate sine x using first principles. To obtain f of x plus h, we substitute x plus h in place.
Sorry, is it just me or the screen is faster than is slower than the audio? Like, hello? Can everybody hear me?
My phone's bad right now,
What?
so I don't. For me, my Wi-Fi is just really bad, so it might be different for other people.
Yeah, like even for me, because this is where I'm playing everything, the voice is faster than what I'm looking at. Is it the same for everyone? Okay, but I hope you guys understand what is being said. Okay, because while this part was being explained, the explanation was faster than what the color coding and everything was displaying. I hope it's not too complicated. It's just what we have just done now. This is going to be 1, and this is just direct substitution. Sine 0 is 0, cos 0 is 1, so this is 0 over 2. Understood? Okay, quickly, let's complete this so we can go.
Of x in the function for f of x. In the numerator, we have the sine of the sum of two angles. Using the compound angle identity for sine, we have the sine of the first times the cosine of the second, plus the cosine of the first times the sine of the second. Notice that in the numerator,
Sorry, can I ask everybody to please concentrate? Some of you are busy writing. You can write later, please. Okay, thank you.
we have terms which involve sine x. We take out sine x as a common factor, and the remaining term involves cos x. From the limit laws, the limit of a sum of two functions is the sum of their limits, provided both limits exist. Since the limits involve the variable h and the variable x is independent of h, we can take sine x out the front of the first limit and cos x out the front of the second limit. Now look at the limits. The first limit is what we found in part A. We know that it is 0. The second limit is the fundamental trigonometric limit, which we know is 1. Simplifying, we find the derivative of sine x is cos x.
Can you see that? This is the result from the previous, you see, it's just showing the last step and the audio stopped already. But I hope everybody gets that. Okay, so I'll send you a screenshot of this also. It's just simple factorization that was done. Okay, so just try to work this out yourself. You see that actually this and this were brought together. Can you see? These two were brought together, then sign was factorized from it. Okay, this minus sign was changed to the second term. Hello, wave your hand if you can hear me, please. Okay, thanks. Then this is the last one. So this is just sin h over h times cos. Then limit of sum is just the sum of limits. And since the limit is the variable, independent variable is h, then anything does not contain h is a constant. You can take it out. It's not affected. Okay, that's why sin x and cos x are taken out of the limit. And why this is the result that was just proved here. So this would be 0. This is the fundamental limits for trig, and that is 1, and you get the result. Does this make sense? Okay, so this is with the idea of first principles, and this is the last thing we want to do. Why is everyone smiling? What's going on? Lillian is smiling like she's gossiping with Karen. She's also smiling. I don't know what's going on. Krista is also smiling like she's part of the gang. Krista K. And Callista doesn't just mind anybody's business. She's just eating food. Don't you all want to be Callista? Like, I don't care what you guys are doing. I'm just going to eat my food. I hope everyone is okay, though. Seriously, what are you guys gossiping about? I'm interested. Like, everyone is just smiling. What's going on? Oh, wait, is it because I'm wearing Topsy's shirt? Is it that obvious? Does it look so much like a female dress, really? I just thought I'd wear something special today. So, how do I look? I look Topsy. Okay, guys, so this is where we stop. Sorry for giving you extra stress. I know you want to like take the day off to just sleep and play with your cat and do whatever. Okay, but we just have to do this so we can like beat the time. Okay, okay, I'll send the video once the conversion is done. I'll send a screenshot right away. I'll see you tomorrow in school and on Thursday in class. Bye bye. I still want to know what you guys are gossiping about though. So talk later. Bye.